There is no need for derivation for the next one. According to the Newton's formula, the speed of the longitudinal wave in a liquid or a gas V is equal to some constant times K isothermal, that is the modulus of elasticity in an isothermal condition, divided by rho. It was so K, that is isothermal. The process is isothermal. So Newton assumed that when the longitudinal wave passes through a medium, the process is isothermal. The temperature is going to remain a constant. That is what K isothermal. So this is the volume elasticity. Volume elasticity at an isothermal condition. So K isothermal is approximately equal to the pressure, because pressure divided by change in volume. Elasticity is always measured as stress upon strain. Strain is not going to have any dimension. So I can write this as C times K isothermal of pressure when temperature is a constant, right? Pressure at constant temperature divided by the density of the medium. But this value of V was found to be somewhere around 220 meters per second, whereas the speed of sound wave in air at STP is 331 meter per second. Then came Laplace correction. Laplace suggested that as the longitudinal wave travels into a medium, it is no more the temperature is going to remain a constant. It is an adiabatic process where your temperature is not going to remain a constant. So the adiabatic process, temperature is not a constant. So he made a correction so that the speed of the wave is gamma times P by rho, where gamma is called Cp by Cv. You know what is Cp? You know what is Cv? Chemistry. That is specific heat capacity at constant pressure by specific heat capacity at constant volume. Now, this ratio for diatomic, monoatomic, and triatomic gases, now it remains a constant. So, Laplace made this correction. That is, he thought that as the longitudinal waves travel through a medium, the temperature of the medium will not remain a constant. The temperature is going to vary. So the correction what he made is that he added the term gamma. So when he calculated, this is the theoretical expression. So when he calculated the value, it approximately came to be 330 meter per second. So which tallies with the experimental value. So right boys, this is your Laplace correction. So the speed of the sound wave or the longitudinal wave in any in gaseous medium, V is equal to root of gamma P divided by rho. P is the pressure, rho is the density. 11B, are you there?
Yes, ma'am.
Just there is no need to derive all these things, boys. You should know, right? What correction Laplace has made. So the velocity of longitudinal wave, especially your sound waves in a gaseous medium, V is equal to root of gamma P divided by rho.
Ma'am,
Yes.
can you explain this again, like in brief?
Okay. That is what. 1 second. See, when sound waves, that is a longitudinal wave, when it travels into a medium, generally it creates a region of high pressure, that is compression, and a region of low pressure, that is called the region of rarefaction or relaxation. Now, generally, what happens is when the region of compression, all your gaseous molecules are being compressed, which means the pressure increases. When the pressure increases, volume increases, and in those region, naturally the temperature will increase. But when the molecules relax in the region of rarefaction, now what is happening is that the molecule, when they relax, their temperature will come down. So that's what Laplace suggested. So as the sound wave travels through a medium, in the region of compression, there will be an increase in temperature, but in the region of rarefaction, where the molecules move far apart, the temperature will come down. So as the longitudinal wave propagates through a gaseous medium, the temperature is not going to remain a constant, which means it is an adiabatic process. So that a correction term has to be introduced. What correction term he has introduced is this gamma. Same equation, V is equal to root of P. P is the pressure of the medium, rho is the density of the medium. Here he added a new term, what we call it as gamma. That is the ratio of specific heat capacity of a gaseous substance at constant pressure divided by specific heat capacity of it at constant volume. I think gamma you would have learned in chemistry, right, boss? Cp and Cv, May's formula.
No, ma'am.
You have not,
No, ma'am.
you haven't learned specific heat capacity May's formula.
No, ma'am. And specific heat capacity is cancelled.
Yeah, ma'am, it's cancelled, ma'am. So we were supposed to learn that in physics, I think so.
You don't know what is and lower grade you have studied. I think ninth grade. Have you studied what is specific heat capacity of specific heat capacity?
Ma'am, specific heat capacity, the amount of heat required to
Raise the
increase the
temperature
temperature
of 1 kilogram
One, yeah.
substance to 1 degree Kelvin of centigrade. Right? If you are doing this at constant pressure, it is Cp. If you are doing this process at constant volume, so specific heat capacity has been deleted for you. Latent heat of steam, latent heat.
Fusion and vaporization we learned in 9th.
Okay.
In 9th,
Here,
latent heat of
here,
fusion and latent heat of vaporization.
yeah. Latent heat of fusion of ice, you know what it meant, what it means, right?
Yes, ma'am.
When ice is going to turn, an ice cube is going to turn into the liquid form, will there be any temperature change noted? Will you note any change in temperature, boss? You take a cube of ice.
When it starts melting, I don't think there's a change in temperature.
Yeah, correct. Once it completely goes into the liquid phase, then you can see the change in temperature. So then the heat hidden, something is hidden. That is what we call it as latent heat. Anyway, boys, I'll just go for the. This is only don't take so much of time over here, boys. This is all the introductory part what we have. So the real subject of the chapter starts now. I'll move on. Now, your chapter of waves starts with this. You'll be studying about progressive wave, boys. You'll be studying about progressive. What is meant by progressive wave? Second, you'll be studying about what are stationary waves, right? And applications, that is stationary waves formed in stringed instruments and stationary waves formed in closed and open organ pipes. So now onwards your chapter, the real concept of the chapter starts. Now what is progressive wave? Progressive waves are the waves which originate from a source. Suppose you have a source, say a tuning fork, right? So now an excited tuning fork means the tuning fork is beginning to vibrate. So when the tuning fork vibrates, now it sends out energy in the form of disturbance. So this disturbance propagating through the medium, we call it as a wave. So now what are progressive waves? The waves originating from a source. Here your tuning fork becomes the source, right? It gives away, it transmits waves to the medium, and these waves travel forward in a medium. Such waves we call them as progressive waves. Right? So these waves advance in a medium with a finite velocity. Yes. You want to note this down?
Not this one, ma'am.
What
is progressive?
Okay.
Yes.
So progressive waves are the waves originating from a source.
Ayan, Siddharth, send it in the chat.
I already did that.
Yeah,
Yes, ma'am, you can continue.
And yes. What we need to do is that, see, when a progressive wave travels through a medium, I don't know. When a progressive wave travels through a medium, it disturbs the particles of the medium. Each and every particle is going to vibrate, right? Now look at this. I'm just talking about the diagram. So say O is the point, that is O is the origin where you have the source. The source which produces the progressive wave is placed at the origin. Then the progressive wave propagates through the medium. Let us consider a particle P. Boys, understand this. You consider a particle P which is at a distance of x meters from the origin. You are considering a particle P which is at a distance of x meter from the source, right? Which is at a distance of x meter from the source. Now this particle is going to vibrate. Now the displacement of this particle at any instant, we have to get an expression for the displacement of this particle. Initially what happens, before the wave propagates through the medium, the particle P would have been at rest. The particle P would have been at rest before the wave is traveling through the medium. Now, when the wave travels through the medium, the wave is propagating, it's a progressive wave. The wave is traveling through the medium with a speed v, and this particle is at a distance of x meters from the origin. So when the wave with a velocity v passes through the medium, it displaces the particle by a distance y. The particle is going to move in the upward direction. Let the displacement be equal to y. It is at a distance of x meter from the origin where the source is being placed. The wave is traveling through the medium with a velocity v. The particle is undergoing a displacement y. Now, the question is, at what time the disturbance reaches the particle P? Here the time, if I take that, time T is equal to 0. So what will be the time at which the particle, at which the wave reaches the particle P? How can I find the distance? Look at this. The disturbance starting from the origin O will reach the particle P in x by v seconds. Is that correct, boss? The disturbance which is starting from the origin O will reach the point P in x by v seconds. What is time? Time is equal to distance by velocity. Right? So what is the distance? At what distance is P from the origin? X meters. What is the velocity of the wave? V. So the disturbance starting from the origin O will reach P in x by v seconds. Correct? Now, what does it mean? In other words, this means the particle P will start vibrating x by v seconds later than the particle at O. Correct?
Right, ma'am.
Diagram at least. Even the diagram is not required. Later on, you can refer only the equation is what we mean for you. So the displacement of the particle at any time t is equal to the displacement of the particle at O at time t minus x by v. Do you understand the statement? Just read the statement. The displacement of particle P at any time t is equal to the displacement of the particle at O at time. Are you getting the above statement? Do you understand this statement? See, if t, okay, no, in case if I give t as 5 seconds, right? Right. So when time was 5 seconds, your particle P is undergoing a displacement, which is equal to the displacement of the particle at O at a time t minus x by, suppose x by v is 1 second. Suppose x by v, which is equal to 1 second. I'll go for 2 seconds. Then this is 5 minus 2, that is 3 seconds. What does it mean? It means that was when the disturbance reaches the point P in 5 seconds, the disturbance would have reached point O in 3 seconds. That is what the statement means. When the disturbance reaches point P after 5 seconds, it would have reached point O, which is a preceding point 2 seconds earlier. It should have reached point, because point O is closer to the origin. So when the disturbance reaches point P after 5 seconds, it would have reached point O 3 seconds earlier. I don't know how much you are getting into second last period. Anyway, boys, so the displacement of the particle P at any time t is equal to, you know, what is the general equation, boys, for displacement of a particle of a medium when wave travels to the medium? It is a sine omega t. Here, your t has to be replaced by t, here, this one, omega t minus x upon v. So I'm just opening the brackets. So what I can do is a sine omega t by, let me go for this term, omega by v. Omega I can write 2 pi nu by v. Your wave equation v is equal to nu lambda, or I can write nu by v is equal to 1 by lambda. So this becomes 2 pi by lambda. Right, boss? So omega by v is equal to 2 pi by lambda. Now lambda is a constant, 2 pi is also a constant. So let us write this as k. So your equation y becomes equal to a sine omega t minus 2 pi, sorry, kx. Should I redo this once again, boys? Boys, I'm just taking this term omega by nu. omega by nu, I can write this as,
No, it's
sorry,
omega by v,
by
right?
v, yes. Omega by v, I can write this as 2 pi nu divided by v. What does your wave equation says? V is equal to nu lambda, or I can write nu by v is equal to 1 by lambda. This I am replacing it as 2 pi by lambda. That becomes equal to a constant, because 2 pi is a constant, lambda wavelength is also a constant. So then this equation becomes equal to y is equal to a sine omega t minus k into x, because omega by v is k. Copy down, boys. Where k is called propagation constant. So now what does this equation gives you? What does this equation gives you? This equation gives you the displacement of any particle of the medium when a progressive wave propagates through a medium. What is a progressive wave? A wave which starts from a source, keeps moving through a medium in a given direction. We call it as a progressive wave. So when the wave progresses through a medium, it makes the particle of the medium to any particle of the, for that matter, it makes the particle of the medium to vibrate. It displaces the particle of the medium. So what is Y? So Y is nothing but the displacement of a particle. Boys, please understand. Y is the displacement of a particle in a time of t seconds, so that it is located at a distance of x meter from the origin. Are you clear, boys? What is Y? Y is the displacement of a particle. Should I put a new screen and explain to you? 11B? 11B.
No, ma'am.
Okay. What is Y? Y is when a wave travels through a medium, it makes the particles of the medium to vibrate. So what is Y? Y is the displacement of any particle. Say here we are taking particle P. So Y is the displacement of a particle which is at a distance of x meters from the origin. Is that not? The particle P is at a distance of x meter from the origin at what time? In a time of t seconds. So in a time of t seconds, your particle P will undergo a displacement of y, and this particle is located at a distance of x meters. Clear? Is that clear?
Yes, ma'am.
We'll do numerical later on. Now this is the principle which is very important, which will be carried over to your grade 12. Principle of superposition of waves. Boys, understand this way. Suppose I have a medium. Clear? A wave is propagating through a medium. Two waves are simultaneously propagating through a medium. So each wave will displace the particle of a medium. Suppose I have different particles of the medium, right? Suppose wave 1 is traveling through a medium. Say I want to check particle P. Right? This is your origin, which produces the wave. The wave 1 propagates through the medium, so that the particle at point P is undergoing a displacement of y1. Simultaneously, another wave 2 is also propagating to the same medium. This wave is also going to displace the particle. Say this wave is displacing the particle to a distance of y2 meter in the upward direction. Then the particle P at the same instant is undergoing a displacement y1 due to wave 1, and at the same time it is undergoing a displacement y2 due to the wave 2. So what will be the total displacement? Total displacement y is equal to y1 plus y2. Was the first chapter in electrical charges of 12th grade starts from this principle of superposition. If you don't understand this concept right now, it will be tough for you in grade 12. Should I redo this? Should I redo this?
Yes, ma'am. Yes, ma'am.
Okay. Boys, you just let me consider a medium, any medium for that matter. It can be air as your medium. So all the particles were initially at rest. I'll take this as the origin. Suppose let me consider a particle P, right? Now, when two waves, let me consider wave 1, a disturbance, and wave 2. Both these waves are simultaneously passing through the medium. What is the character of this wave? It will make the particle to vibrate, or it will make the particle to undergo a displacement. Say wave 1 is going to make the particle to move y1 meters in the upward direction. Now, simultaneously, another wave is also traveling, right? So in a time of t seconds, wave 1 is making the particle at p2 undergo a displacement y1. At the same time, the second wave is making the particle to undergo a displacement y2. So at the same instant, both the waves are making the particle to undergo a displacement y1 and y2. Then what will be the total displacement? The total displacement is given by
y1 plus
plus
y2.
y2. It's a vector quantity, boys. It's actually a vector quantity. Because if it is the downward direction, it will be negative, right? Now, this is what we call it as a principle of superposition of waves. If the first particle, say, if y1 is plus 5 centimeter, y2 is plus 6 centimeter, then your y will be equal to 11 centimeter, which means the particle will move in the upward direction 11 centimeters. Suppose y1 is 5 centimeter, y2 is minus 2 centimeter. Then your y becomes equal to plus 3 centimeter. It will vibrate 3 centimeter above. So copy down this principle of superposition of waves. The principle of superposition states that when two or more waves, right, two or more waves meet at a point, the resultant displacement at that point is equal to the sum of the displacement of the individual waves at that point, right? So y becomes equal to y1 plus y2. So what is y? Y is the resultant displacement. No need for a diagram, boys. You can just write the statement. Y is the resultant displacement. Y1, what is y1? Displacement due to wave 1. What is y2? Y2 is displacement due to wave 2. What do you have last period, boys? P 11B.
Yes, ma'am. P.
Yes, ma'am.
Then anyway, you'll not. For the other class, I'm almost completing this chapter. I'm just lagging behind. No, I'm not disturbing your PE period.
Ma'am, anyways, we don't do anything in PE.
Ma'am, but if you can give us our P, we wouldn't mind attending P class.
If you give physics period.
No, ma'am. He said if you were physically able to go for, go out and play, then we wouldn't mind PE classes.
But now, what I mean is that, boys, because if I can complete, I have almost completing this chapter for 11C. So might be on Sunday, I'll be completely finishing it off. So, but only your class. Now, once you finish this, then the next 3 derivation will be very easy for you. It will not be tough. Otherwise, on Sunday, I have to borrow classes. I don't know, Sunday I might be having 12th practicals. I should not run short of your periods. Let's just copy down. The principle of superposition states that when two or more waves meet at a point, anyway, I'm not taking full period of your PE. I'll take only just 10 minutes of your PE period, boys.
Ma'am,
Yes,
sir
ma'am.
takes attendance, ma'am, so we have to be present. Otherwise, he'll mark us absent.
No, it's fine, ma'am. We don't exactly even do anything in PE.
No,
yes,
what I'll do. No, who is your PE teacher? I will just.
No, ma'am. Sir doesn't like start the meeting itself. It's like a synchronized
Yeah,
class.
these days it's mostly asynchronous.
So you just tell me, boys. I can put a request message. For 10 minutes, I'll just take your period. Then I'll leave you.
Yes, ma'am. It's fine, ma'am.
Who is here? Rajesh Yadav, sir?
Yes, ma'am.
Rajesh
Not
Yadav.
Rajesh.
No,
Raj-
say
Raj-
not Rajesh Yadav. The other Rajesh. Sir.
Rajesh Gopinath, sir.
Okay. Fine. Let me just. Oh, it's almost time. Is it time? It's almost time.
Yes, ma'am.
Boys,
It's
can.
pretty much all the
Yeah,
time.
ma'am, 1
Sir,
minute.
what I'll do, I'll not close this meeting. Can someone log into your PE class? Just can you get the permission and come back so that substantial amount I'll finish it off, boss.
Ma'am, until he starts, you can keep going on. When he starts, I'll join the meeting. I'll say and I'll come back.
Anyway, superposition of waves. So you started with progressive wave. Then next is principle of superposition of waves. Now comes your stationary waves. Now, what are stationary waves? Now, suppose a progressive wave.
Ayan, your mic.
Boys, if a progressive wave is traveling into a medium in positive x direction, then suppose it encounters a reflector. Reflector means the wave travels. It can be a rigid wall also. So a progressive wave is traveling through a medium, say in positive x direction. Then it gets reflected by any reflector. The reflector can be a wall also, any material. So when it gets reflected back, then you have another progressive wave traveling in the opposite direction. So what happens? Both the waves are going to overlap. Overlap means superpose each other. So when they overlap each other, you will get what we call it as stationary waves or standing waves. Are you clear, boys? Now look at the statement. Stationary waves or the standing waves are produced by superposition. Superposition means overlapping of what? Of two progressive waves of equal amplitude, which means both the waves, one which is traveling along x direction, positive x direction, the other one is traveling along negative x direction. Now, both the waves should have the same amplitude, should have the same frequency, and traveling with the same speed in the same medium but in the opposite directions. This should happen. Both the waves should have the same amplitude, should have the same frequency, should travel with the same speed, but the wave should travel in the opposite direction. Now, if this happens, both the waves will superimpose each other. Can you see, boys? Suppose the wave which is marked with blue in this diagram, the wave which is marked blue is the, say, the progressive wave which is traveling, or the green one, whichever wave. So the blue one, will take it as traveling in the positive x direction. It gets reflected back. When it gets reflected back, you can see the green, the wave which is marked with green. Now these two waves, one traveling forward, one getting reflected back, they superimpose on each other. When they superimpose on each other, you will get a pattern like this. And such waves which are produced are called stationary waves. Now, this stationary wave has two important characters. Look at this, boys, these points. Now, these points are called nodes. Now, what are nodes? Nodes are the point where the displacement of the particle is zero. The particles which fall at these nodal points will be at rest. Then you have antinodes, which are marked as A. Now, antinodes are the point where the particle will undergo maximum displacement. So what are stationary waves? Stationary waves are the waves which are produced by overlapping of two progressive waves. Both the waves should have the same amplitude, same frequency, traveling with the same direction, but in the opposite direction. Yes.
So in the diagram, it's wrongly mentioned, right? That antinodes and nodes.
Yeah, I think so. That's the previous one. Here it's
Not this diagram. The
no,
other
not the previous one. Yes.
Yes.
So stationary waves have yes.
Ma'am.
Okay, you can leave.
Ma'am, our PP started. I'll just go in. Oh, okay.
Just check with sir and come back.
Yeah, I'll inform sir.
If sir is not allowing, then I'll close this.
Okay, ma'am.
Ma'am, could you show the previous slide for a second?
This is what happens, right? One end is fixed, this end is fixed. So the wave travels like this. Now this fixed end becomes a reflector. So now the other wave, reflected wave will move in the opposite direction. So as a whole, you'll have a standing waves, or what we call it as stationary waves. Now at nodes, these are the points we call that. Point B is a node. At node, none of the particles will vibrate. At antinodes, point A, all the particles which fall at point A will vibrate with maximum amplitude. There are three derivations. Those things are important 3-mark questions from this chapter, boss. This chapter will carry 3-mark question. So you will be, let us see the standing waves produced, different modes of standing waves produced in a stretched string, then organ pipes, all those things we need to do. Just check if sir is stating that it's very important for you.
Ma'am?
Yes?
Ma'am, I just came up from the PE class. He said it's fine. We can continue with the time.
So I'll go with the derivations, because the important derivations what we have here is stationary waves in a stretched string. The first one, stretched string, I think so only few of you have done the experiment. That is for sonometers. I don't remember how many of you from your class has done this experiment. Boys, now look at this, boys. You have a string. All your stringed instruments like guitar and all, you use your string. I think those who use your musical instrument, you will know. You will there are knobs which you tighten, which means you're increasing the tension. Anyone who plays guitar in this class? Someone who's playing guitar in this class can speak up. No one. Okay, fine.
Yes, ma'am.
I'm Steve. Ma'am, Steve plays, no?
Steve, don't you change the tension of the string?
Yes, ma'am. Yes. To increase the frequency. Yes, ma'am. Yeah.
Yeah, you will change the tension. That's all, right? So now look at this, boys. The experimental setup is like this. You have a string. Now this end of the string, one end of the string is fixed. You can see here. The diagram will be better, right? So what? Suppose I'll put this end, a fixed end, right? The other end of the string, you're applying a load so that the string will be under tension. Only when the string is under tension, if you pluck the string begins to vibrate. So you have a string, say, of length L meter, stretched under tension. So you're putting a load. Now this load will create a tension in the string. this end of the string is fixed. The fixed end of the string. The string is going to have a length L. So the other end of the string is attached to a load. So the string is under tension. So M is the mass per unit length of the string. Now the speed of the transverse wave on the string is this much. Now what is that you're going to find? Now you can make the string to vibrate in different mode. What are the different mode? You can make the string to vibrate in different modes. In each of these modes, you can find the frequency of the string. Because whether you understand this, you can make the vibrate in different mode. I'll just go for the video clipping. You can make the string to vibrate in different mode. Each mode of vibration, in each mode of vibration, you can find the frequency with which the string is going to vibrate. Find the frequency. So in each mode of vibration, your string will vibrate with different frequency. Before going for this, I'll just go for the clipping. Boys, can you see the video clipping? Boys, can you see the video?
No, ma'am.
Can you see the video clipping?
Yes,
Oh, yes, ma'am, but the audio is not.
Audio is not. For 1 second.
Yes, ma'am.
1 second.
Ma'am, is it fine if you can upload this video in the file because like the 10-minute thing is over?
Okay, fine.
Ma'am, like we can watch it like after school or something.
I'll just go for because you should know what are the different modes of vibration.
Okay, for this demonstration, I have my able assistant, Parker. Parker, smile at your admiring audience. And we will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where there's approximately no motion going on. 2, 1, 2. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone. Let me try again. Okay, I think I've got it approximately now. I think I had it for a little while there. That's the third mode, where the
So what you're going to do is that you're going to create different modes of vibration in a stretched string, and then you're going to find what is the frequency of the vibrating string in different modes. Are you clear, boys? Here you're going to
10
create
minutes,
different.
10 minutes.
Yeah, that's it. I can finish it off, boys. So you're going to create different modes of vibration, and then you'll find the frequency of each mode. So start with this, boys. Start the statement. Consider a string of length L stretched under a tension of T. Let m be the mass per unit length of the string. Then the speed of the transverse wave. You can expect this question. It's an important remark question. Then the speed of the transverse wave on the string is v is equal to root of t by m. So you all want to go for PE class. I'll go for only one mode of vibration, then I'll leave you, boys. Fine. Okay. If you want to write it later, you can write it later. I'll go for the first mode. Let me finish only first mode, then you can know. First mode of vibration. In your first mode of vibration, what? If this is your string, you're creating a wave. So these two are the fixed end of the string. This point.
Ma'am, can you show the previous slide?
Okay, this is.
Oh yes, ma'am. Oh yes, ma'am.
Okay, this is the first mode of vibration. Now keep this in mind, boys. If I have a wave like this, right? The wave pattern. So between a node, and a node, consecutive 3 nodes, the distance is lambda. Always understand this. If I have 3 points, a node, and a node, then this distance, entire distance is lambda. Same thing goes for antinodes also. The distance between 2 nodes is lambda upon 2. The distance between a node and an antinode is lambda upon 4. These are the things which you should understand. The distance between 3 consecutive nodes is lambda, or the distance between 3 consecutive antinodes is lambda. The distance between 2 nodes is lambda by 2. Distance between a node and an antinode is lambda upon 4. So here you're creating a mode of vibration where you have the wave which is formed on a string. Now the string has a length L. This is your string. Both the ends of the strings are fixed. You are creating a mode of vibration where you have 2 nodes and an antinode. So then what will be the distance between them in terms of wavelength? Between 2 nodes, it becomes equal to, between 2 nodes, the distance is lambda by 2. Yes or no, boys?
Ma'am, could you show the previous slide, please?
Right, boys? I think so. You're finding it difficult to concentrate. If you want to join your PE class, join so that Sunday, possible, hope so, I'm not having any 12th grade practical session in the morning, then I will take up your class teacher's period. Fine, boys. I think so. You're finding it difficult. Just copy down this and then I'll go for it. Sunday, how many periods I do have? 11, 2 periods I have. I'll take class teacher's period. Fine, you can go for your PE class. Those who have completed, go, boys.
Thank you, ma'am. Thank you, ma'am.
Thank you.
Thank you, ma'am. Thank you, ma'am.
Thank you, boys.
Thank you, ma'am.
Sunday,
Thank you,
I'll
ma'am.
just.
Thank you, ma'am.
Thank you, boys.